Hey everyone, it's Mark again and welcome to the second part of Elk-Stack webinar. Today we will take a closer look to the first use case scenario, which is usage of Elk-Stack as full-text search engine, and during that we will also unhide some mysteries behind Elasticsearch indexing process. Let's go! So, full-text search, what that might be? If we want to be really simplistic, we can reduce it to something like that.
Yes, that's the search bar. So UI is pretty simple. We want some box where users write their query. The query is then sent to the server and some black box will find desired results, which are then displayed back to customer. Okay, now there are two things we should define. First, what is the black box that gives us results? Yes, very good guess. That's the Elasticsearch. We create query to Elasticsearch. It will go through all index documents and give us result. But most of the time, we just don't want the 1000 results long list with every document containing some word. We or our customers want most relevant results, results that are sorted so that first result are most likely the ones we are looking for. And that's to mention second thing, sorting and relevance. Well, the goal of sorting is simple. We want to give users most relevant results first, so there is high chance they will find what they were looking for. Or in case of e-commerce, he will most likely to buy given result. So good sorting might have a significant impact on revenues. But there's a catch, and you probably know what it is. Each implementation requires different and custom tailored sorting. That means we have to set different weights on different fields in index documents. In case of web pages, it might be, for example, to set higher weight on page title, headers like H1 and H2, or some custom tags. The marketing department might even want to have ability for manual results ordering or precisely its weighting. Motivation in that case is clear. They want to promote some product in a manner that it is higher in the search results. Luckily for us, Elasticsearch gives us a lot of functionalities to control result scoring. Okay, what we want to achieve is clear. Now let's find out how to do it using Elasticsearch. First of all, there is out-of-the-box hosted solution for full-text search directly from Elastic. It's called Elasticsearch. It is hosted by Elastic and it has a lot of useful features and a very nice administration interface where you can set various options. That's the easy way how to achieve our goal.
If you cannot use hosted service because of, for example, legal reasons, or you just want to make full-text search build an Elasticsearch on your own, you have to solve two problems: how to get data into Elasticsearch and how to get the results from Elasticsearch. To push data into it, you can just send the content from your CMS through REST API. This way you will search over CMS content and your full text search will be very closely integrated with your CMS. You can, for example, put an input field in your content edit page to set custom scoring. Another benefit is that the edited content will be modified also in Elasticsearch almost in real time.
The problem might come when you don't want to search over your CMS content, rather over web pages, where the content is located. If you don't see the difference, I will explain an example. You might have article which is placed on two different web pages. In case of CMS content search, you will find this article only one time. In case of page search, you will find all pages where the article is located. In other words, the index document identifier in case of CMS content search is some content ID. In case of page search, it is URL and it is the way how, for example, Google works. Now, how to index whole portal? Simple, using web crawlers. There are numerous open source web crawlers like Apache Notch, Stormcrawler or Heritrix and others. Crawler will get seed URL, which is most usually your homepage, loads it, parses it and indexes it. During processing, it will find all URLs and in next iteration it will load content of all found URLs. That means crawling job most usually runs few times a day and loads content of all pages. In modern crawlers, there are some optimization of this process implemented. For example, the database of links is stored between crawler runs, and crawler only checks if the content of this page has been modified using if modified since header with date of last crawl run. During content processing, it is recommended to store parts of web page which are significant for scoring into separate field, that is most usually title, h1 and h2 headers, and maybe some meta headers. We can then easily say Elasticsearch that if queried word is in the title, the document has much higher score than if it is only in text. Okay, so crawler prepares documents with filled-in content, probably looking like this. Crawler then calls Elasticsearch's API with pull request. The last part is just URL encoded in string, and Elasticsearch will know it is the document ID. And then the Elasticsearch will store it inside its index. Okay, now let's talk a little bit about Elasticsearch indexing. Elasticsearch holds data in indices. This is sort of wrapper for index documents. Index is split into pieces called shards. Each shard of one index can be and probably should be stored on different Elasticsearch node in case of multi-node cluster, of course. This way the search query runs in parallel and is much faster. But we should be aware of performance cost that comes with each running shard. Actually, each shard is separate instance of Apache Lucene, so it is fully functional Search engine on its own. Shards are then split into so-called segments. Segments contains the inverted index over which the search is performed. Because segments are immutable, Elasticsearch holds incoming data in memory and every now and then refreshes the search and stores them to file system, creating new segment. During the time it holds documents in memory, they are not searchable yet. Only after the search refresh, they become searchable. This time frame can be modified using refresh interval setting of index. These segments are written to disk after the so-called flush. Elasticsearch performs also the segment cleanup operations, so the data are not split into too many segments. This is called segment merge, and as the name suggests, Elasticsearch merges multiple segments into one. All of this runs automatically in background. Okay, now how does Elasticsearch parse incoming data? The process of parsing is called analysis, and it has text data on input and tokens or terms on output. The analysis consists of three lower level operations: character filtering, tokenizing, and token filtering. The analyzer's definition is stored in index setting. That means most of the time in our index template. And one point to mention, although we are talking about indexing, such analysis definition can be defined also for search queries. That means query text is also processed by analysis. Now back to analysis steps. The first one, character filtering. Character filters are used to modify incoming text data. For example, if we want to remove all HTML tags, this is the right place to do it. Elasticsearch comes with some prepacked character filters like mentioned HTML strip filter or pattern replace filter. After character filtering, the tokenizer takes place. The tokenizer breaks text into tokens using defined set of rules. The most obvious tokenizer rule is splitting on space, so hello world is split into hello and world. Again, Elasticsearch contains several prepacked tokenizers like letter tokenizer, which breaks on non-letter character, h-engram tokenizer, which is very useful for search as you type feature because it breaks text from beginning up to defined length. So hello world string and max length 4 and min length 0 will come, or maybe 1, will become the H, HE, HEL, HELL. One good point to mention, analysis can have only one tokenizer defined. When text is broken into tokens, the token filtering takes place. Token filters have tokens on input and they can add, remove or modify them. One of the most used examples is lowercase token filter, which turns all characters in all tokens into lowercase. Another very useful token filter is ASCII folding filter, which replaces all accented characters with their unaccented alternative, like you see on the screen. There are numerous useful token filters prepackaged with Elasticsearch. You should check the documentation. And that's it. After token filtering, tokens are stored into Lucene inverted index and later flushed to disk in mechanism described earlier, and we can execute search queries over them.
Regarding queries for full-text search, that is something so specific to your needs that there is no single correct answer, but most of the time you will use match phrase prefix query for search as you type queries, and function score query for standard search feature. You should definitely check official Elasticsearch documentation to find what suits you the most. And that's all. We described the use case that was at the very beginning of Elastic's stack, that is full-text search engine. I hope you enjoyed this part and see you at the next one where we will take a closer look at the second use case, log centralization, and we also check some details about beats and log stage. Have a nice day.